Do alien worlds host life? It is a question that has guided scientific inquiry for decades, shaping how we observe the universe and define our place within it. Rather than approaching this problem with speculation, modern astronomy follows a structured method. Scientists search for planets where conditions resemble those on Earth, where stable temperatures, liquid water, and the right chemical elements can exist long enough for life to emerge. Tonight, we focus on a system that has drawn sustained attention for a very specific reason. It is not simply distant or unusual. It offers a rare combination of accessibility and structure that allows detailed investigation. This system is known as TRAPPIST-1, located approximately 40 light-years away. In astronomical terms, this is relatively close, enabling precise observation using advanced instruments. What makes TRAPPIST-1 particularly significant is its planetary arrangement. It contains multiple Earth-sized planets orbiting a single ultra-cool dwarf star. Several of these planets lie within what scientists call the habitable zone, where temperatures could allow liquid water to exist under suitable atmospheric conditions. This is not a single candidate world, but a system of several potentially comparable environments. Here is an important teaching insight. When multiple planets share the same star, they also share similar formation conditions. This allows scientists to compare how small differences in distance or atmosphere affect planetary evolution. In effect, TRAPPIST-1 functions as a controlled natural experiment, something extremely rare in astrophysics. The arrival of the James Webb Space Telescope has significantly improved our ability to study this system. Unlike earlier telescopes, JWST can analyze the light passing through planetary atmospheres during transits. This allows scientists to identify gases such as carbon dioxide, water vapor, or methane, each of which provides clues about environmental conditions. To understand the importance of this, consider a simple example. If light from a star passes through a planet's atmosphere, certain wavelengths are absorbed depending on the molecules present. By measuring these absorption patterns, scientists can reconstruct the chemical composition of that atmosphere without directly seeing the surface. This is the stage we have now reached. The question is no longer whether such planets exist. The question is what conditions actually exist on them. Are these worlds stable, volatile, or potentially habitable? As we examine the data from this system, we are not searching for immediate answers, but for measurable evidence. Each observation refines our understanding, narrowing possibilities and revealing patterns, and this naturally leads us forward. If these planets are so accessible and structured, what exactly has the James Webb Space Telescope revealed about their atmospheres and conditions? To understand the conditions within this system, we now turn to its central star, TRAPPIST-1. Everything that follows, every planetary climate and atmospheric possibility, is ultimately governed by this single source of energy. TRAPPIST-1 is classified as an ultra-cool red dwarf. In terms of size, it is only slightly larger than Jupiter, yet it contains far more mass. This distinction is important. Size alone does not define a star. Mass determines the pressure and temperature at its core, which in turn controls how energy is produced and released. Red dwarfs are the most abundant type of star in our galaxy. A useful teaching insight here is that when we look up at the night sky, most of the stars that actually exist are too faint to be seen. TRAPPIST-1 belongs to this hidden majority. These stars burn their fuel very slowly, allowing them to live for trillions of years. To put this into perspective, the universe itself is about 13.8 billion years old, meaning a red dwarf like TRAPPIST-1 will outlive the current age of the universe many times over. At first glance, this long lifespan might seem ideal for life. More time could mean more opportunity for biological processes to develop. However, the situation is more complex. Because TRAPPIST-1 is relatively cool, its habitable zone lies extremely close to the star. Planets in this region orbit at distances much smaller than Mercury's orbit around the Sun. This proximity introduces a critical effect known as tidal locking. In simple terms, one side of the planet constantly faces the star, receiving continuous light and heat, while the other side remains in permanent darkness. An everyday analogy would be the Moon's relationship with Earth, where we only ever see one side. For a planet, this creates strong temperature contrasts that can challenge atmospheric stability. Another factor must be considered. Red dwarfs are known for intense stellar flares, sudden bursts of radiation that can strip away planetary atmospheres over time. Without an atmosphere, a planet cannot retain heat or protect potential life from harmful radiation. So, while TRAPPIST-1 provides a stable, long-lasting energy source, it also introduces conditions that can work against habitability. The balance between these opposing factors becomes central to our investigation. Interestingly, not all red dwarfs behave identically. TRAPPIST-1 shows signs of being less active than many of its counterparts, suggesting a more stable environment than expected. This raises an important question. If the star is relatively calm, how have its planets evolved under these conditions? To answer that, we must now examine how this entire planetary system was first discovered and mapped in detail. If the star defines the environment, the next step is to understand how the planets themselves were first identified with such precision. This brings us to a method that, at first glance, appears almost indirect, yet has proven remarkably powerful. Transit photometry. The principle is straightforward. When a planet passes in front of its host star, it blocks a small fraction of the star's light. Instruments measure this slight dimming as a dip in brightness. By observing these dips repeatedly, scientists can determine not only the presence of a planet, but also its size, orbital period, and relative distance from the star. A useful way to visualize this is to imagine a small object moving across a bright lamp. Even if the object is too distant to see directly, the change in light tells you it is there. In astronomy, these changes are extremely subtle. For TRAPPIST-1, the variation in brightness is often less than 1%, requiring highly sensitive instruments and repeated observations. In 2017, using this technique, astronomers combined data from ground-based TRAPPIST telescopes and the Spitzer Space Telescope to reveal a complete system of 7 planets. All of them are roughly Earth-sized and composed primarily of rock. This alone is unusual. Most planetary systems discovered earlier were dominated by gas giants or planets unlike anything in our solar system. A teaching insight here is worth noting. Discovering one Earth-sized planet is scientifically valuable. Discovering 7 within a single system allows comparative analysis. Scientists can observe how small differences in distance from the star influence temperature, atmospheric retention, and surface conditions. It is similar to studying multiple variations of the same experiment rather than relying on a single result. Perhaps the most striking feature of this system is the distribution of these planets. 6 of the 7 orbit within what is called the habitable zone, the region where temperatures could allow liquid water to exist on a planet's surface under the right conditions. This does not guarantee water or life, but it establishes a necessary starting point. However, proximity to the star introduces complexity. These planets orbit very close together, with orbital periods ranging from just a few days to a few weeks. Such compact arrangements lead to gravitational interactions that can affect internal heating and orbital stability. So while the discovery of the TRAPPIST-1 system provides an exceptional set of candidates, it also raises deeper questions. Are these planets truly capable of maintaining stable environments, or do their close orbits introduce conditions that work against habitability? To answer that, observation alone is not enough. We must examine what surrounds these planets, particularly their atmospheres, and for that, a new level of observational capability becomes essential. To move beyond identifying planets and begin evaluating their true nature, a more advanced observational approach becomes necessary. Detecting a planet tells us that it exists. Understanding its atmosphere tells us what it is like. This distinction is crucial. This is where the James Webb Space Telescope becomes central to the investigation. Unlike previous instruments, it is specifically designed to study faint infrared signals with extremely high precision. For a system like TRAPPIST-1, which emits relatively low light, this capability provides a significant advantage. The key method used here is known as transmission spectroscopy. The concept is logical if we consider what happens during a planetary transit. As a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere before reaching the telescope. Different gases absorb different wavelengths of light. By analysing which wavelengths are reduced, scientists can identify the chemical composition of that atmosphere. A simple way to understand this is to think of light passing through coloured glass. Each colour absorbs certain wavelengths and allows others to pass. By studying the transmitted light, one can infer the material of the glass. In the same way, astronomers read the atmosphere of a distant planet through the signature it leaves on starlight. A teaching insight worth noting is that this process does not rely on directly seeing the planet's surface. Instead, it depends on precise measurement of very small changes in light. These changes are often measured in parts per million. This level of sensitivity requires both advanced instrumentation and repeated observations to confirm results. TRAPPIST-1 offers a unique advantage in this context. Because the star is small and dim, the relative effect of a planet passing in front of it is more pronounced. The signal from the planet's atmosphere becomes easier to detect compared to systems with larger, brighter stars. As a result, the data obtained can be up to 10 times more sensitive than similar measurements in other planetary systems. This improvement is not merely technical, it changes what can be studied. Instead of broad assumptions, scientists can now search for specific molecules such as carbon dioxide, water vapor, or methane. Each of these has implications for temperature, atmospheric stability, and potential biological processes. However, it is important to maintain clarity here. Detecting a molecule does not confirm life. It only indicates the conditions that might support it. Interpretation requires careful comparison with known physical and chemical processes. With this level of precision now available, the focus shifts from the system as a whole to individual planets. Each world must be examined separately, beginning with those closest to the star, where conditions are expected to be most extreme. With the ability to examine atmospheric signatures in detail, attention naturally shifts to the planets closest to the star, where conditions are expected to be most extreme. These inner worlds provide an important test of how proximity to a red dwarf shapes planetary environments. TRAPPIST-1b and TRAPPIST-1c were initially considered promising due to their Earth-like sizes. Early assumptions suggested that such planets might retain thick atmospheres, potentially moderating their surface conditions. However, direct observations have led to a different conclusion. Measurements indicate that TRAPPIST-1b reaches surface temperatures of approximately 227 degrees Celsius. At such temperatures, most known biological molecules would become unstable. More importantly, data shows little to no evidence of a substantial atmosphere. Without an atmosphere, heat is not distributed effectively, and the surface remains exposed to direct stellar radiation. A useful comparison can be made with Mercury in our own solar system. Mercury lacks a significant atmosphere, resulting in extreme temperature variations between its day and night sides. TRAPPIST-1b likely experiences similar, if not more intense conditions due to its closer proximity to its star. TRAPPIST-1c presents a slightly different case. It appears cooler than initial models predicted, which might suggest more favourable conditions. However, observations again show no clear signs of a dense atmosphere. This absence is critical. Temperature alone does not determine habitability. Without an atmosphere, there is no mechanism to retain heat, circulate gases, or shield the surface from harmful radiation. A teaching insight here is essential. Planetary size often leads to assumptions about similarity to Earth, but size alone is not sufficient. Composition, atmospheric retention, and stellar interaction all play equally important roles. Two planets may appear similar in scale, yet differ completely in environmental conditions. These findings carry broader implications. They demonstrate that even within a system rich in Earth-sized planets, many may fail to meet the basic requirements for life. Proximity to the star, combined with stellar radiation, can strip atmospheres over time, leaving behind barren, exposed surfaces. This does not reduce the importance of the system. Instead, it refines the search. By eliminating less favourable candidates, attention can be directed toward planets where conditions may allow more stable environments. As we move slightly farther from the star, the balance between temperature and atmospheric retention begins to shift. The next planet in sequence offers a more complex and uncertain case, where habitability cannot be dismissed so easily. As we move slightly farther from the star, the pattern becomes less definitive and more nuanced. The next planet, TRAPPIST-1d, occupies a position that places it near the inner boundary of the habitable zone. This location alone suggests that its conditions could differ significantly from the harsher inner worlds, yet the available data does not lead to a simple conclusion. Current observations do not provide clear evidence of a stable atmosphere surrounding TRAPPIST-1d. At first glance, this might suggest conditions similar to the inner planets. However, there are indirect indications that the situation may be more complex. Some models allow for the presence of a volatile, rich layer, or even a subsurface ocean concealed beneath a dense atmospheric or icy shell. To understand why this matters, consider how heat is distributed on a tidally locked planet. Without an atmosphere or ocean, heat remains concentrated on the side facing the star, while the opposite side becomes extremely cold. This creates a sharp thermal gradient that limits the possibility of stable surface conditions. However, if a planet possesses an ocean or a sufficiently thick atmosphere, these can act as mechanisms for heat redistribution. A useful analogy is Earth's own climate system. Ocean currents and atmospheric circulation transport heat from equatorial regions toward the poles, preventing extreme temperature differences. If TRAPPIST-1d has similar internal or atmospheric processes, even in a simplified form, it could reduce the impact of tidal locking. A teaching insight here is that habitability is not determined by a single factor. It emerges from the interaction of multiple systems, including atmosphere, internal structure, and orbital dynamics. When one piece of data is missing, such as direct atmospheric detection, scientists rely on indirect evidence and modeling to explore possible scenarios. Another important consideration is the planet's energy balance. Being closer to the inner edge of the habitable zone means it may receive more stellar radiation than Earth does from the Sun. Without protective mechanisms, this could lead to atmospheric loss or surface heating beyond stable limits. Yet with the right conditions, that same energy could support dynamic processes such as liquid water circulation beneath the surface. This ambiguity makes TRAPPIST-1d particularly valuable from a scientific perspective. It represents a boundary case where small changes in atmospheric composition or internal structure could shift the planet from inhospitable to potentially habitable. As we continue outward, the diversity of planetary environments increases further. The next set of worlds introduces not only different temperature regimes, but also entirely different compositions, including planets where water itself may dominate the structure. As we extend our view farther from the star, the nature of these planets begins to change in a more fundamental way. The environments are no longer dominated solely by heat and atmospheric loss. Instead, composition itself becomes a defining factor. TRAPPIST-1f presents a striking example. Current models suggest that this planet may contain a significant fraction of water, potentially up to 20% of its total mass. This is far greater than Earth, where water represents only a small fraction of the planet's composition. Under such conditions, water does not simply form oceans, it can exist as a deep global layer, possibly extending hundreds of kilometers beneath the surface. However, this does not automatically create a habitable environment. At such depths, pressure increases dramatically. Water can transition into high-pressure ice phases that do not behave like familiar ice. Above this layer, a dense, steam-rich atmosphere may form, trapping heat and creating a high-pressure surface environment. A useful teaching insight here is that water alone is not a sufficient condition for life. On Earth, life depends on the interaction between water, atmosphere, and solid surface. If water dominates too completely, it can isolate chemical processes that are essential for biological activity. Moving outward, TRAPPIST-1g shows evidence that makes it particularly interesting. Observations indicate the possible presence of water, though not necessarily in the extreme quantities suggested for TRAPPIST-1f. Its position within the habitable zone places it in a range where temperatures could allow liquid water under the right atmospheric conditions. This introduces an important balance. Too little atmosphere leads to instability, as seen in the inner planets. Too much water or atmospheric pressure can create environments that are equally restrictive. TRAPPIST-1g may lie somewhere between these extremes, making it a candidate for further investigation. At the outer edge of the system lies TRAPPIST-1H. This planet likely receives very little energy from its star, resulting in surface conditions that are predominantly icy. However, theoretical models allow for a possibility that may seem counterintuitive. If the planet possesses a hydrogen-rich atmosphere, it could trap enough heat to maintain liquid water beneath the surface, or even in localized regions. A brief example from our own solar system helps clarify this. Moons such as Europa and Enceladus are believed to contain subsurface oceans beneath thick ice layers. These environments are not exposed to direct sunlight, yet internal heat and pressure create conditions where liquid water can persist. The outer planets of TRAPPIST-1 demonstrate a critical point. Habitability is not a single pathway but a range of possible configurations, each with its own limitations and uncertainties. Among these varied worlds, one planet occupies a position that balances many of these factors more precisely. It is neither too close nor too distant, neither too dry nor overwhelmingly dominated by water. To understand the strongest candidate for life in this system, we must now examine that planet in detail. Among the planets in this system, one occupies a position that aligns most closely with the conditions we associate with habitability. TRAPPIST-1e lies near the center of the habitable zone, receiving approximately 2/3 of the energy the Earth receives from the Sun. This balance places it in a range where liquid water could exist, provided other conditions are favorable. This energy level is significant. If a planet receives too much radiation, surface water may evaporate or be lost to space. If it receives too little, water freezes permanently. TRAPPIST-1e exists within a narrow interval where temperature could allow stable liquid water, at least in principle. Observations from the James Webb Space Telescope provide further insight, though not definitive answers. Data suggests that TRAPPIST-1e may possess an atmosphere. Importantly, this atmosphere does not appear to be dominated by light gases such as hydrogen, which are commonly found in gas-rich planets. Nor does it resemble the thin carbon dioxide-heavy atmosphere of Mars. This leaves open the possibility of a more balanced, Earth-like atmospheric composition. A teaching insight here is essential. When scientists search for life-supporting conditions, they are not looking for exact copies of Earth. Instead, they look for combinations of factors that can maintain liquid water, moderate temperature, and chemical stability over time. TRAPPIST-1e appears to satisfy several of these criteria, at least partially. However, the data also introduces complexity. There are indications that methane may play a role in the planet's atmospheric behavior. Methane can act as both a greenhouse gas and a cooling agent, depending on its interaction with other atmospheric components. In certain configurations, it can reduce surface temperatures rather than increase them, potentially making the planet colder than expected. This highlights an important point. Atmospheric chemistry is not a simple system. Small variations in composition can lead to large differences in climate. A planet that appears ideally positioned in terms of distance from its star may still develop conditions that are less favorable for life. Another factor to consider is surface and internal activity. If TRAPPIST-1e has geological processes such as volcanism, these could replenish atmospheric gases and support long-term stability. Without such processes, even a favorable atmosphere might gradually be lost. Taken together, these observations place TRAPPIST-1e at the center of scientific attention. It is not confirmed to be habitable, but it represents the closest known example of a potentially Earth-like world within this system. Yet even in this case, favorable conditions do not guarantee the presence of life. There remain significant challenges that must be addressed before any conclusion can be drawn. To understand these limitations, we must examine the environmental constraints that affect even the most promising candidates. Even with its favorable position and possible atmospheric presence, TRAPPIST-1e must be evaluated within the broader set of physical constraints that govern planetary environments. Habitability is not determined by a single promising feature, but by the balance between supportive and destructive processes. One of the most important concepts here is the idea of localized habitability. Because TRAPPIST-1e is likely tidally locked, one side of the planet constantly faces the star while the other remains in darkness. Under such conditions, a region known as the terminator zone, the boundary between day and night, becomes particularly significant. In this region, temperatures may be moderate enough to allow liquid water to exist, even if the rest of the planet experiences extreme conditions. A useful comparison can be made with Earth's polar regions. While the poles are cold and receive less sunlight, they still support limited ecosystems due to localized conditions. Similarly, TRAPPIST-1e may not require uniform habitability across its entire surface. Life, if it exists, could be confined to specific regions where conditions remain stable. Another possibility involves subsurface environments. If water exists beneath the surface, protected by layers of ice or rock, it may remain stable regardless of surface conditions. This concept is supported by observations within our own solar system, where moons such as Europa are believed to host oceans beneath their icy crusts. These environments are shielded from radiation and temperature extremes, creating potential niches for life. However, these possibilities must be weighed against significant challenges. The host star, despite being relatively calm compared to other red dwarfs, still produces stellar flares. These bursts of radiation can erode planetary atmospheres over time. Without a strong magnetic field or sufficient atmospheric density, a planet may gradually lose the very conditions required to sustain life. A teaching insight here is that early stellar activity plays a critical role. Red dwarfs are often more active in their early stages, emitting higher levels of radiation. If TRAPPIST-1e lost its atmosphere during this early period, it may not have been able to recover it later, even if current conditions appear more stable. This introduces a key limitation in our observations. We see the planet as it is now, but its history determines whether it ever had the opportunity to develop stable, life-supporting conditions. Thus, TRAPPIST-1e represents a balance between possibility and constraint. It may support regions where life could exist, yet it may also have faced conditions that prevented such development entirely. To reach a final conclusion, we must consider not only what is possible, but what is most likely given all available evidence. This leads us to the broader assessment of the entire system and what current data can and cannot definitively tell us. When all available evidence is considered together, the picture that emerges is one of possibility constrained by uncertainty. TRAPPIST-1e remains the most compelling candidate within this system, yet current observations do not allow a definitive classification. It could possess a stable atmosphere, internal geological activity, and conditions suitable for liquid water. Equally, it could be a barren world that lost these properties early in its history. This uncertainty is not a limitation of scientific reasoning, but of available data. The James Webb Space Telescope has extended our observational reach significantly, yet it operates within measurable limits. Atmospheric signals remain faint, and distinguishing between different chemical compositions requires repeated observations and careful interpretation. A useful teaching insight here is that science progresses through refinement rather than immediate conclusions. Each observation reduces the range of possibilities, narrowing the set of viable explanations. In the case of TRAPPIST-1, we have moved from speculation about distant worlds to direct measurement of their atmospheric properties. This represents a fundamental shift in how such questions are approached. Future instruments are expected to extend this capability further. Concepts such as the Habitable Worlds Observatory are designed to detect more detailed atmospheric signatures, including potential biosignatures. These are chemical patterns that, when found together, may indicate biological activity rather than purely geological or chemical processes. However, even with improved technology, interpretation will remain essential. The presence of certain gases does not automatically confirm life. Each detection must be evaluated within the broader context of planetary physics and chemistry. What TRAPPIST-1 ultimately provides is not a single answer, but a structured framework for investigation. 7 planets, each with distinct conditions, allow scientists to test how variables such as distance, composition, and stellar influence interact to shape planetary environments. This system represents a transition point in our understanding. We are no longer limited to asking whether Earth-like planets exist. We can now examine how common they are, how they evolve, and under what conditions they may support life. In this sense, TRAPPIST-1 is not just a target of observation. It is a reference system that informs how we interpret similar discoveries across the galaxy. The final conclusion, therefore, remains open. Current evidence neither confirms nor excludes the presence of life within the system. It establishes that the conditions required for life may exist, but it does not yet demonstrate that they do. The question has evolved. It is no longer whether life could exist elsewhere, but when observational precision will allow us to confirm it with confidence.